Okay, we'll go back and look at it. Okay, so thermochemistry, what does thermo mean? Heat, okay? So we're going to be doing stuff with heat. We've got thermochemistry now. Later in the book, we have a chapter called thermodynamics, which are very, very closely related. So energy. Energy is not a new concept. You've seen potential energy and kinetic energy before. Potential energy is energy of position or composition. So the higher you drop something from, the more potential energy it has before you drop it. You know, so dropping something from, 6 inches height, right here, this stylus only has potential energy, and it's going to land here, so it doesn't have very much potential energy. I'm dropping it here, it has more potential energy. So position. Composition, that's more the one we're focused on in chemistry, because that's when we're looking at the energy in chemical bonds. But either way, potential is stored energy. It's not being used, but it's there to be used. Okay? Kinetic energy is the opposite. It's energy of motion. Law of conservation of energy. Energy can neither be created nor destroyed, but may change form. So potential turns into kinetic. Kinetic can then cause potential energy. So they can go back and forth. Now, potential and kinetic are the two broad terms for energy. Heat energy, light energy, all of those other types of energy are just subcategories. And everything can be changed from one to another. When you have mechanical energy, moving parts, a side effect is it produces heat. Okay? Energy is a state function. What that means is the pathway doesn't matter. Okay? If you're going from here to here, if you go by that route or you go by this route, it doesn't matter. The only thing that matters is where you started and where you finished. Okay. Whenever we are talking about thermochemistry, it's very important to define or identify your system and your surroundings. Okay? And the system is just simply what you care about. The surroundings are everything else. So if you are looking at, you have a cup of ice water and you're looking at the temperature as it warms up. Well, your cup of ice water is what you've defined as your system. So everything else is your surroundings. If your ice is melting and so the temperature of your system is increasing, it must be getting that same amount of heat from the, I've got two choices, system and surroundings. It's getting it from the surroundings, okay? So you're going to be looking at, if your system is losing heat, the surroundings are gaining the exact same amount. If your system is gaining heat, it's gaining that amount from the surroundings. The surroundings are losing that. So you will have the same number with a different sign. So you can measure the system and then extrapolate that to the surroundings if that's what you need. When we're talking about thermochemistry, we're talking about a lot of times is something endothermic or exothermic. So think about those words. The prefix exo, what does the prefix exo mean? Out, like external, exit. Got a lot of things, okay? So if your reaction is exothermic, heat is being released. So the system is losing heat. So it would be negative for the system, and the surroundings are gaining that heat. Heat will always be a product, so on the right side of the equation. And if we draw an energy diagram, see these right here, those are the reactants. These are the products. Energy's on the y-axis. The products have less energy than the reactants did because the reaction gave off heat. Now, endothermic is, of course, the opposite of exothermic. And endo, like enter, means in. So endothermic is when it is absorbing heat. Now, an exothermic reaction will feel warmer because if it's going on in the beaker and it's releasing heat, the surroundings are gaining heat. Well, if you're touching the beaker, you're a part of the surroundings. So, hot packs and cold packs. Are hot packs exothermic or endothermic? Exothermic. And cold packs? Endothermic. Okay? When you pop that bag and mix the two chemicals, that mixing is endothermic. It must absorb heat from the surroundings. Well, the part of your body with the injury where you set that ice pack, that's the surroundings. It's absorbing heat from you. That's why it cools. So since heat is a reactant this time, it's going in. See how reactants, maybe what that is. See how reactants are here and products are here. So we have increased the potential energy now because energy has been absorbed.